So I've got,
Can you just turn those off?
yeah, feels like we're in a cheap motel.
Yeah.
Lighting problems today. So I've got some in-class exercise. I'm not sure what you guys want to do. There's in-class exercises in assignment 15, which is not going to be on a test or any exam or anything like that, but might be fun to tackle some problems with resonance or transformers.
Oh, problem solving session?
Yeah.
Oh, great.
It's not a lecture today, it's problem session today, and tomorrow, I think also, well, tomorrow maybe I can do the lecture, a little bit of a lecture on the other transformer lecture, which is, I'll have to think about that. Because then, Monday and Tuesday, well, also we could do problem solving if you have any questions on homework 14, which is due Friday.
Oh my god, yeah, it is, huh?
We can work on that. So
This is homework 15?
this is homework 15, it's optional. It's going to be extra credit, and I was going to have some quiz questions related to this that you can tackle.
Did you figure out how you're going to implement that yet?
No, but another idea just came to mind. Maybe I will use Christopher's software for this. It might be easier.
Oh, that's neat.
Yeah, for what I'm thinking of. But it might be... Yeah. Actually, maybe I could use, I could probably use this Christmas. You know, I could have the answer be a string of numbers, 1, comma, 0.1, comma, 6.25. You have to get the digit. Of course, you could just guess it just by changing the values. That's not going to be good.
You would at least have to.
It has to be some kind of a challenge. So, no, I don't know. Since most of these have multiple, well, this one only has one answer, so this would be a killer one, right? You have to get the average power. So this would be a great quiz one, knowing how to do this. Yeah, this, something that has one answer would be great.
Quiz 8 is due Sunday, right?
Quiz 8 is due Sunday, yes. Yeah. So we could look at quiz 7 if there's any questions you have on that, or quiz 8 review questions. What do you guys think is more valuable for you? There's also a practice test 4. I thought we would kind of pull that out next week, like maybe Monday or Tuesday.
Let's do that next week.
Yeah.
Yeah. Probably Monday. Because Tuesday we got all that lab stuff going on.
Tuesday's a lab, that's right. Yeah, so we only have, right, yeah, we only have 3 more lectures before test.
Oh my god.
Yeah. Should we just take a nap instead
Tom,
of...
can it just be over?
I know. I'm having the craziest day today. I had to get up at like 5:30 to take my mom, haul her to the airport.
Oh, where's she headed?
San Diego to get some tests. She's having some issues. And then I had a meeting right after that. I had time to get breakfast, which was nice. But then this afternoon, I have 2 conference calls, and I'm filling in for Matthew's MATLAB class. Be a pretty busy day. Oh, and I have a awards ceremony. There's some kind of a teacher appreciation thing going on at the Hilton.
Hey.
Yeah.
You're getting recognized?
I guess. I don't know.
Hey! Yay, Tom.
Thank you. Thank you.
Remember,
I did it all myself. I didn't have any help at all.
That's what I'm telling people. Are you guys going to have another party like you did at the end of last semester with that cheese that was really good and all the snacks?
What party?
The faculty thing that you had at the end.
Oh, yeah, the potluck, yeah. When is that? That's probably this Friday, right? Oh, no, next Friday, last week of class, yeah.
I might have to swing by to drop off a homework assignment or something.
I think. No, you know what? I don't know, because we have this barbecue. I think it might just be subsumed by that. I don't know what the deal is. I don't know if we're having a potluck or not. Anyway, here are practice problems for homework 15. If you don't give me a better idea, we can do those.
Let's do that. Yeah.
And I think we're going to need some formulas up here, so I will put a screen up. Oops, I need not that one, but so the first two are about resonance circuits. Sine series RLC with omega 0 given. And so this would be basically a filter. You're trying to emphasize using resonance signals with a frequency of 40 radians per second and a bandwidth of 10. That's the bandwidth of the resonance. And by the way, there's a really cool, are you guys interested in wasting time? There's a really cool video of, it's an astronomical resonance. And they made a, so they're trying to figure out, so there's this star, it's only 40 light years away from us. And it has, it's a dwarf star, a red dwarf, I guess, I don't know, which is, not very bright. So there's 7 planets in the habitable zone, which is pretty close to the star. So they have pretty quick orbits, like a couple days or something like that. And a system with this many planets so close together would supposedly be unstable, except that they seem to be locked with resonance. So it maintains, they think it maintains a stability through some kind of orbital resonance. And some researchers did this thing where they turned the orbits into notes, and they produced a musical track of the system, and it's really cool. I was just listening to it this morning. You gotta check it out. They bring in the different planets one at a time. Becomes kind of a fugue. It's like the music of the spheres. And they make a drum beat whenever they're all lined up or something like that. James like, what's going on? You should never leave the classroom, man. It's something cool. So this is a real system 40 light years away from us that has 7 planets locked in an orbital resonance. And it's the most musical system because of the ratio of the orbits.
What is happening there?
A drum beat, like whenever they are in sync.
Oh. That's awesome.
It makes amazing music. Isn't that hilarious? I guess those are solar flares, huh? Random solar flares. Probably wouldn't want to live there. Yeah. Anyway, so that's your inspiration for resonance, even though electrical resonance is a lot more boring than that.
No way.
So back to the formulas. If you have a, so one of those involves a series resonance and the other one involves a parallel resonance. And series resonance, the formulas are here. So it's kind of like, second order circuits, right? Isn't this is just alpha plus alpha squared. So omega 0 is always square root of 1 over LC. So that will pin down your omega 0, whether it's series or parallel. And then the bandwidth is minus r over 2L plus essentially the square of those alpha squared plus omega squared, and then plus r over 2L plus the square root of alpha squared plus omega squared. And the bandwidth is the difference between those two frequencies. So if you're doing, so these are pretty easy extra credit if you find these close to.
Sorely want.
Yeah. And you actually can pick, because there's so many variables, you would probably have to pin down one or two of these things first and then find the third one. So for instance, you know the omega 0 is 40, right? So, wait, is this series? Yeah, that one's a series. So omega 0 is 40. So you would write down the equation that, 1 over the square root of LC has to equal 40, because that's the resonant frequency. Yeah, there you go. Omega 0 is always 1 over the square root of LC. So it has to be 40 for the first problem. And then the bandwidth has to be 10. So that looks like, well, maybe not that easy, because you got to do some solving here. So, and the answer is given to you, but I think you might want to sort of, let's see. I think you might want to, well, set, have our agreement setting the magnitude of z equal to, yeah. You basically have sort of a nonlinear system of equations, essentially, right? So omega 0 is the square root of 1 over LC, which is 40. And then the difference, so the bandwidth, the bandwidth, well, also, can we use this formula? We know that the bandwidth has to be 10, and that has to be the difference between omega 2 and omega 1. So actually, if you take omega 2 minus omega 1, what do you get? You end up just getting, because this cancels out, so it's going to be it's basically r over L, right? If you subtract omega 2 minus omega 1, right? So that equals 10. So you have two equations, you got three unknowns, which means I think you can pick one and then just solve for the other two. Does that make sense? So they're kind of fun that way. So so try picking. So if you know for this one, omega 0 equals 40 equals 1 over the square root of LC, and we know that omega 2 minus omega 1, which equals essentially r over L, is going to equal 10. So you have to figure out a way to come up with some numbers there. So if you assume r is 1, that pins down L, right? And then once you know what L is, you can solve for C. But what if you assume that R is 10? So maybe, why don't you guys try a few different numbers and see if you can come up with reasonable designs for that, right? So Emma, you could try R equals, what if you chose R equals 10? And Duncan, you want to try like R equals 100. And see what we get for numbers.
So Tom, if we're looking at a circuit diagram, is there something that we can see at a glance to know that it's a resonating circuit, or would that actually just require going through the equations on an AC circuit?
Is there a way to know if something is a resonant circuit at a glance? That's a good question.
Like, because we can tell if something's an AC circuit immediately. But
basically, I mean, if it has an L and a C in it, it's a second order circuit, and it could be resonant, but resonance only. It might have to do. No, I think. See, you know how the second order circuits have those different dampings and stuff, and I'm thinking a resonant circuit is probably underdamped. Probably needs to be underdamped. But that would be a good question to kind of answer. If you have a circuit that's say overdamped, would that be resonant? What would be the frequency response of that? And that's actually, it's pretty easy to kind of test those assertions with FreeMat, for instance. Like if you come up with the R's, the L's, and the C's, we can plot the frequency response real easily in FreeMat, and then you can kind of see, look at the resonance and see if that makes sense. And then you could come up with other values that are not necessarily chosen to be resonant, and then see if you still get a bulge in that thing somewhere. Like, for instance, if we could find an RLC circuit that's overdamped.
So it has to have an inductor and it has to have a capacitor.
Well, but that's just one typical pattern. But you could also, if you have capacitors that are independent in the circuit, they could also be resonant, but not if they're right next to each other, because then they're going to combine.
Yeah. If we had a RLC circuit where the L and the C were in series, but they were in parallel to the rest of the circuit, and we use a switch to disconnect the resistor and the source, and we're just left with an LC circuit. And that would cause the charge to bounce back and forth infinitely, wouldn't it? Or?
It would if it was super cool, because the inductor has a resistance in it, and the capacitor is leaking current too, so they're not ideal. But
so would that be with that little area there? That would be sustained resonance at that point, right?
Yeah, they have demonstrated that in superconducting applications. They can make that thing ring.
And in the real world, what we would see if we were watching it as a waveform, we would see a waveform that's slowly losing its amplitude.
Losing energy, yeah.
To zero.
In the real world, yeah.
Cool.
So it'd be like, like ringing a bell, right? You smack a bell and it rings, ding, and then it gradually over a long period tapers. But that bell is resonant, and it's keeping that thing going because it's storing the energy and putting it back in, and storing it and putting it back in.
Now, if that switch did the same thing, but the only thing it cut off was the source instead of the resistor, so we just have the RLC without a source in it, that same thing would happen, but much quicker.
Yeah. The resistor would absorb the power more quickly. So, he's so deadpan, yeah.
Well, yeah, he only laughs. It's like a punctuation. So they're like, huh. Are you doing the MATLAB thing to try and test the?
Yeah. So this is what's cool about MATLAB is you can make these inline functions, and
Tom, remember how you told me you should hire me as like the spokesperson for your intro class? I think MATLAB should hire you as the spokesperson for MATLAB.
Oh, they have a lot of people that are spokespeople for MATLAB. So you say, I've got this add is like an anonymous function. You don't have to make a function file, which is really nice. You assign, well, H is going to be some function of omega, R, L, and C, and then it's just going to be 1 over, and if I'm going to use a vector, I think I need to do that. 1 over square root of R squared plus W times L minus 1 over WC. And that becomes squared. And we're doing the square root of that. I think that is it. Yeah. So what's great is you can set, so this is going to give us essentially the transfer function of any RLC circuit. And I can come up with a vector of omega. So like this is supposed to be resonant at omega equals 40. And I could say, well, let's let omega go from like 0 to 100. That's probably good enough. Then I can find out my my magnitude of the response is going to equal the absolute value, because this is going to be, no, that already is a magnitude. It's going to be h of, we're going to give it this vector, and then give me some r, l. So I'm going to give those, the ones in this problem solution they had was 1.1 and 6.1, 0.1 and 6.25 millifarads. And this gives me all of the points on that transfer function, which I can then plot. I can say plot omega and what I call it, mag. And that's the frequency response, right? It's really nice. This is why you too one day will be promoting MATLAB, because it's just so easy to go from just an equation to a curve. And then the Q is the ratio, and you can kind of look at these, the 70% power points and the subtraction of those things are supposed to be about 10 apart, right? So if you go to that 0.7 point and 0.7 point, that's going from like 35 to 45 approximately, right? Which is 10. So that's the bandwidth. So now if you come up with your own numbers with different R, L, and C, which I'm curious, are we going to get the same response or something different?
Save that picture.
Yeah, so I'll save this, and I'll give it a title so we don't get them mixed up.
Yeah. Where's your title and your labels? And
Yeah, this is what I mark people off for. Series R equals 1, L equals 0.1, C equals Oh, this must be another, what? This is a different MATLAB session? I think I have two.
No.
I've got two free mat windows open here.
One MATLAB is enough.
No. You can't have too many. MATLAB is why we have these online quizzes. I've been doing all the problems in MATLAB. And why they are mostly correct, but not all of them. These are all the solutions to the online quiz in MATLAB.
Oh, so I shouldn't be taking pictures of this? Or?
No, you shouldn't. So let me put that in this new one here. Okay, so this is So did you guys get any numbers? Did you get a number, Duncan?
Yes.
So this is,
You go first.
let me put it in a Word document so I can come back to it. Okay, so what'd you get, Duncan? Did you use an R of 1?
Yeah.
With 100? Wait, so what'd you get for L? Is that right? Wait, because that's the same numbers as the other one. But I think that's, wait, so well, no, because see, if your R is 100, then your L has to be 10, right? Because R over L has to be, yeah. So your L has to be 10, and then your C has to be something else.
You want the values that we got?
Yeah, what'd you guys get?
For R equals 10, we got that L is 1 and C is 0.65 millifarad.
0.65 millifarads, okay. Okay, so now what's cool is we can just do, and what's awesome, even more awesome than that, in FreeMat, you can pull up the old, actually we can do this plot, and instead of plotting WMAG, we can just plot W and H of W, and R was 100, L was, wait, your R is 10, right? 1, and that's 0.625, E minus 3, right? And we do that, and we go instantly to plot. And this is the new plot. And it looks.
We can get both plots on the same graph.
Yes, you can, and I'm glad you asked. Because you can do a subplot. And should we do them vertically stacked or horizontally stacked? Probably vertically stacked, right? We can see them one on top of the other. So it'll be, you want to do like 3 rows and 1 column. And the first plot will be the one with an R of 1. So we'll say, so MAG is still where it was. So let's just do that one. So you plot W and MAG, and then you do the title. And then we can change the subplot. Well, you can see you've got that one. Wait, why did it get flipped? That's weird.
Ah, I can see. Yeah, I don't think that's resonant.
No, there it is.
Oh.
Probably because it was a really small. This screen resolution is probably messing up the software. That's the problem with these high-def screens. And then we can change the subplot to the second one, which is 3, 1, 2. And then reactivate this command for the second filter, and I think we'll see that they are identical. Weird.
Oh, yeah. They are.
Are they exactly identical? Looks like they may be a little bit different.
They look the same.
If there is anything different, it looks like a little bit smaller.
See, this one looks a little higher here, doesn't it? Or is that my imagination?
You can use MS Paint to overlay them.
Well, you can also subtract these things, right? So you can say, well, what is the difference? Is going to be MAG minus this thing. And they are, what's the multiplier? There's usually a multiplier in front of this. No, actually, so there's some difference, but it's not very much. Well, actually, no, because the scale on this is from 0 to 1, right? So there's about 12, that's about 13%, 15% at the most, 20% difference.
You think you'd be able to see
25, 20, yeah, 23%, 28, 30%, what?
You think you'd be able to see that though, right?
Let's go up here, 40%.
60%?
It's peaking at a 68% difference.
88%?
So, oh, the better thing,
90%?
rather than subplot is to plot them on the same curve, right? So let's kill this whole subplot thing.
Yeah.
And subplot 1, 1, 1. We'll get rid of all that, and then we can just do our plots cascading. So we can do plot W comma mag and W and that, and
Well, that's completely different.
oh right, and that's because the bigger R suppresses it more, right? I think that's the deal, right? Because this is the R was 10, right? So Duncan's will probably be even smaller. So when you look at it in that respect, it looks like it has a smaller Q, but I'm not sure if that's true or not. Maybe not. Maybe that's not true. And then, you know, what's typical with frequency responses, it's typical to plot them on a decibel scale, and that shows a broader range of values better. So the decibel scale is 20 times the log 10 of the magnitude, and this will show you when you have a broad range. So that's interesting. And it shows you, when you go, a 10 decibels represents a power of 10, I think. So, oh wait, that's 20 decibels, so that's, I guess 20 decibels is 1 power of 10. So you can see they have the same shape, but they are quite a bit different in terms of amplitude. And so, Duncan, did you get values?
Yeah.
What'd you get?
I'm using 62.5.
So let's do one more. We do all three on the same. So we got W. Let me just copy. So you got an R. You had an R of 100, an L of what? 10. And 6200 was C.
Yeah.
62.5 microfarads. Oops. So there they all are. That's another 20 decibels lower. So yeah, but the same shape, right? And they all satisfy the criteria of the problem, which was that. But you can see, yeah, if you want more gain, you'll get, I guess, lower resistance. So, so the parallel one is kind of a similar deal. Which you can do if you want, but it might be more interesting to try this one. We have about 13 minutes left. The value of the average power absorbed by the 8 ohm resistor. And for this one, they've got this, these dots. I think we can ignore the dots, but they affect the polarity of the voltages. So I think, like, if you're doing this, I think the ratio, I always forget this, but I think the plus sign for V1 goes here then, and the plus sign for V2 goes here. The way they're wound, and our N here is, so the N here is, it looks like it's 1/3, right? It's usually 1 to N, where N is 1/3. And the question was, what's the question again? What's the average power absorbed by the 8 ohm resistor? Right, so to get that, we need to find I2. And, well, let's see. Can we use... So this is where, that transformer is changing the impedance of the load to something else, right? And according to our lecture yesterday, which is this lecture, you've got this deal where the impedance looks at 1, the impedance that you see in the first circuit, the primary, looks like the impedance of the load divided by n squared. So you can use that to find I1, and then the ratio will tell you what I2 is, and from there you can find the power in the dissipated by the resistor, right? Does that make sense? So the plan of attack for this one would be, you can reduce this to Z1 is going to equal ZL over n squared, right? So that's going to be effectively what that load looks like in the primary, right? And then you can, so that's your step 1. Step 2 is going to be solve for I1. And then step 3 is going to be, I2 is going to equal, what's that ratio again? So if you look at this, what they're saying, this is a step-down transformer because the secondary coil has fewer turns than the primary. So the voltage is going to be 1/3, so V2 is going to be 1/3 of V1. That means the I2 is going to be 3 times, it's going to be 3 times I1. So once you find I2, then the average power is going to be, let's see, you've got the, it's going to be, so P is going to be the RMS squared times 8. I2 RMS squared times 8. Well, I guess, let's see. And actually, they don't tell you. I think it looks like it's not RMS because they're not giving us phasors. So I think it's going to be I squared over 2. The magnitude of I2 squared over 2 times 8.
So it's just 4i squared then?
Yeah, 4I2 squared. So, but the steps are going through and finding, our ZL. And of course, we've got to put this all in the phasor domain, right? So omega equals 30. We could change it to a cosine, but I'm just not sure you have to for this because they're asking for the average power, and the power, whatever, the phase kind of doesn't really, let's see.
For an average, the phase wouldn't matter, right?
Yeah, you just need the magnitude of the I. So I think you can ignore that. If you want to, there's no harm in keeping that in there though, so.
I mean, yeah, because just changing it would just...
So this would be 160, or instead of actually changing it to a sine, you can just keep your, when you do the inverse phasor transform, you go back using sines instead of cosines, if you needed to get a time waveform. But yeah, so the you could say this is one angle. Is it minus 90? And then this is going to be minus j over 30 times 1 over 120. And that is going to equal, was that minus 4j? So ZL is minus 4j, right? Well, actually, it's 8 minus 4j. And 1 over n squared is going to be 1/9, or n squared is going to be 1/9. So this is going to be basically 72 minus 36j. That's the impedance in the primary of that. So we can solve for I1. Should I just do this? You guys are feeling pretty lethargic, and I'm pretty lethargic too. Been a long semester.
It's a gray, dark day.
It is. So I1 is going to be and good old Freemat will get this done really fast. So we can do the and we want to do the mag phase of I1. I've got a different mag phase here which prints it as a complex number, but this is the angle, so it's 1.944 with an angle of 64, minus 64 degrees. That's your I1. So I2 is going to be 3 times that, but let's see. And that means it has a magnitude of 5.8329. And according to our understanding of power, then we can take I2, square it, and multiply it times 4. I think I'm off. Let's see. So 5.83 squared times 4 is 135, and the answer is supposed to be like 58 or something.
Yeah, we got like 172.
Is that anywhere related to what we have?
So, I mean, do we need to change the trig function? Would that have been it?
Off by 2.3. Well, this is changing it. 160 angle minus 90
Oh, yeah, you're right.
is a cosine. So that's not it. What else did we do wrong here? Let's see. Oh, you know what? I think I did my I1 wrong, right? Because there's actually the 48 ohms in here too. I forgot about that. So the Z1 is 74 minus 36J because that's 9 times our ZL. But then I1 is actually V over the total impedance, so it's 48 plus 74 minus 36J.
Oh, okay.
Thanks for all your help, guys.
It's 126.
Sorry, was that Duncan? Did I do this wrong? 72, yeah, not, I can't, there you go. 72.
That was my mistake.
So I1 then is really going to be, let's go back up here and redo that statement. I1 is going to be 48 plus 72, what is that, 120? Suspiciously nice number there. And then I2 is going to be 3 times that. So we only have 3.83. So then we have to take that. And we get the answer. Yay.
What?
Okay.
Yeah.
You got to be good, right? As you know, to get these things to get the right answer is
We use free apps.
something to be celebrated.
Quiz.
Yeah, it's really easy, but you can't use it. Well, you can use it for the quiz, yeah, but the quiz is supposed to kind of show you what you've got. You got to be able to do that with a calculator on the test.
Is this going to be on the final?
This, no. It's not even on test 4. You do have to know complex power, though. So there is some complex power in here, so that's on test 4.
That's not too bad, though.
No. So tomorrow, what do you want to do tomorrow? Should we do the lecture on the assignment 16, or
I was thinking.
just do more problems? You could do, so we could do quiz 7 practice or quiz 8 practice problems.
Ooh,
We could do,
I wouldn't mind doing quiz 8 practice problem.
yeah, that's going to help you on test 4 too.
Yeah, things to help prep for test 4 would be nice.
Yeah,
I've got a lot riding on that test.
I know. Everybody does.
Don't want to take the final.
But I want you to take the final.
Well, I'm going to take the final no matter what, but I don't want the stress of taking the final. If
Good.
That makes sense.
I agree. You probably do better without the stress. Oh, I don't know. Some people do well under stress.
I'm not going to tell you where I do my best because I don't want you withholding information.
Sure.
Sure. Let's get cool.
So the assignment due tomorrow.
14 is due tomorrow, yeah. Yeah, so we could work on that too if you have any questions for me.
Yeah, I'm gonna be in Davis tomorrow.
Oh, you're going out to Davis. Cool. Awesome.
So
Can you turn it online or? Are
I
you,
might not be able to turn it that night.
okay. You just email it to me.
Opening Saturday.
Just email it to me, yeah.
Tom, this might be kind of a bad question. I'm going to ask, would there be any way, I know I waived the right, but would there be any way I could see the letter of recommendation?
Oh, yeah, but I think Stanford proves that it wasn't the letter that did it.
Well, I mean,
It's
Dr. D
something
could have
else.
wrote a really, so for Stanford, I think I had Russia, Dr. D, and
Okay.
Philly. And for MIT, I had Russia, Philly, and you.
Yeah, what was interesting about yours is that they said you could do a letter, but they encourage you to kind of do like writing to prompts.
That
So
seems like a good idea.
I just basically wrote the answers to the prompts, and they're like, well, in case I ever need to make a letter out of this, I saved the answers to the prompts, but it's not really in a letter form. I could show you that if you want.
Yeah, sure. I want to see what you wrote. I just want to see what the teachers wrote about me. Would you mind emailing it to me, or?
I could email it to you, I guess, yeah.
No, I appreciate
Sure.
that.
All right. Mm-hmm.
Yeah.
Yep.
I usually have fans everywhere.